Alright, so lesson 7 on this unit is continuing on what we started last time with graphing exponential functions. This time we will be including some transformations. Now the transformations are the ones you are familiar with. A is at the front of the equation, K is up in the exponent, D is a subtraction inside the bracket of the exponent, and then C is external to the whole thing. Note, b is not a transformation parameter. B is part of the parent function. Remember? So let's just make a note of that quickly. B is not a parameter. Rather, it is part of the parent. Okay, so that's part of the parent function that b is coming from. All right, so looking at this one, so just a little bit of review. If you have a number bigger than 1, where b is, you're going to get exponential growth. If you have a number in between 0 and 1, you're going to get exponential decay. So it's, it'll be dropping over time as opposed to rising. Okay? Now, when you go to stretch these things and use all these different so we're going to compare 2 to the x with 3 to the 2x and 0.5 and so on. And we've already talked about this one, but let's just quickly go back over it. So I'm going to change my f of x function to 2 to the power of x. I'm going to, no need to show the, well, sure, we can show the original. Now my c value is 0, my d value is 0, my k value is 1, and I'm supposed to adjust my a value. Okay, so let's make a 1, and you can see you get exponential growth, and it goes through 0, 1, 1, 2, and 2, 4. Okay, so compare the function with all these other ones based on the table below. Okay, so you can see that if I make a large number, it causes the graph to rise more rapidly, or if it's a large negative number, it falls more rapidly, right? So it gets steeper. The y-intercept gets farther away from the x-axis, and the function itself rises more quickly. Okay? If you choose a fraction in between 0 and 1, you have a vertical compression. Okay, so let's just go back and answer this. So if absolute value of a is greater than 1, so this would be a vertical stretch by a factor of a occurs. Remember, let's just write in brackets. Absolute value of a greater than 1 means a bigger than 1 or a less than negative 1. That's just what absolute value greater than 1 actually means. It means the number you're thinking of could be a positive number bigger than 1, or it could be a negative number smaller than negative 1. Okay, now if 0 is in between a and, if the absolute value of a is in between 0 and 1, you get a vertical compression. Remember, what does this mean? 0 less than absolute value of a less than 1 means negative 1 is less than a, which is less than 1, and a is not 0. So, in other words, a is some number between negative 1 and 1, but not 0. Okay, that's what that means. That's another way of writing it in the absolute value notation. If a is negative, then again, as always, the function is reflected in the x-axis, as in up to down. Okay? Now, what about when we include a d value? Okay, so here it's asking 2 to the x, 2 to the x plus 2, 2 to the x minus 2. Alright, so let's set a back to 1. And now let's start moving d. Now when you move d, basically, if you look down here, all the y values are identical. All the x values have moved over by 2. And what does this look like in terms of the function? The function has been shifted 2 to the right. Notice again, it's x minus 2 because it's x minus d. If I make d a negative number, now I have x minus negative 2, and what you're going to see in the bracket is x plus 2. Once again, the y values are completely unaffected, but all the x values have shifted over to the left. Okay, so again, so all we're doing here is, you already know the answer to this, but just to see what it looks like in an exponential. If d is bigger than 0, a horizontal translation of d units to the right occurs. And let's just put an example, 2 to the power of x minus 2. In that example, d is a positive 2. Okay. If d is less than 0, then a translation of d units to the left occurs. And again, a quick example of that would be 2 to the power of x plus 3. In that case, d would be the number -3. Okay, now kx is a tricky one. As always, k is there's a little bit more thinking involved with k than with the other ones. So let's reset it. So we'll set d back to 1. Excuse me, d's default value is 0, not 1. And then let's try manipulating k. Now again, you might think this is making the graph taller like a did, but it isn't, right? It's making this part taller, but it's actually making this part shorter. And a didn't do that, right? Let's go back to a for a second. If you notice, a drags the whole thing up. Okay? K doesn't drag the whole thing up, only one side. The other side actually goes down. Now again, the better way to think about this is not actually in the vertical sense at all. Think of it in a horizontal sense. This graph and this graph are the same. They've just been horizontally squished together. So like the point that used to be out here gets squished into here. The point that used to be here gets squished into here, right? And so what you're actually looking at here is not a vertical change, but a horizontal change. Look at the y values. The y values haven't moved. The x values have all been compressed by a factor of 1/2. So 2 becomes 1, 1 becomes 0.5, 0 remains unchanged, -1 becomes -0.5, and so on. Now if k is a fraction, right, think of this point as being stretched out to here, and this point being stretched out to here. So the function's being pulled apart left to right. Once again, the y values are unaffected, and all the x values have doubled. And what this looks like in terms of the pictures, it looks like the graph is being stretched out. Now, interestingly, when k becomes negative, the graph has the same issue. So a fraction stretches it out, a 1 makes it look the same, and a high number like 2 or 3 make it horizontally compressed. But the negative k switches it from growth to decay. You might want to think about why. Why would it do that? It's a really good question to think of here. How does a negative k change the function from growth to decay, or vice versa? How did it do that? How did it change the function that was growing in an exponential way to a function that is now shrinking in an exponential way? All right, so let's put in what we have here. So if k is bigger than 1, then you have a horizontal compression by a factor of 1/k occurs. So for example, 2 to the power of 2x, k is equal to 2, but the English sentence is a compression by 1/2, right? By 1/k. Remember, k is 2, the sentence only has the 1/2. Okay? If k is in between 0 and 1, you have a horizontal stretch by a factor of 1/k. So again, an example of this would be 2 to the power of, let's say, 0.2x. Here, k is equal to 0.2. We would say that this is an expansion by 5, because 0.2, when you When you put 1 over 0.2, you get 5. Again, I would correct this a little bit. Let's put absolute value symbols here, the same way it was with a. If k is negative, the function is reflected in the y-axis. And again, I might also think of this as growth to decay and vice versa. Okay? So some things to think about there with k. Now C is interesting. C changes something that nothing else changes. So one of the things that all of the functions I've drawn have in common is that every one of them has a horizontal asymptote down here, right? I can change D. I can change K. I can change A. And none of those things moved that red dotted line, right? None of them moved the horizontal asymptote. Now, on the other hand, C, which is going to vertically shift the function up and down, you can see that if I shift the function up, that asymptote should really be coming with me, right? And if I shift the function down, that asymptote should be coming with me in a downward direction. So instead of calling this asymptote y equals 0, I'm going to call it y equals c. Now when I move c, the asymptote comes with me, and you can see that it's always in the right place. So for example, in this equation, 2 to the power of x take away 3, the asymptote is at negative 3 now, because that's the c value, and that's where the asymptote is. Okay, so let's write down what we've learned about c. If c is greater than 0, you have a vertical translations of c units upward. And if c is less than 0, you have a vertical translation of c units downward. And the equation of the horizontal asymptote is always y equals c. So whatever c is, that's the only number that influences your asymptote, and it controls everything about it. Again, your transformation function that you remember, hopefully, from earlier in the course still works. Every x becomes x over k plus d. Every y becomes ay plus c. And then you will always transform these things correctly. Let's go through one together. We'll go through a couple. I mean, it's what we're doing today. So let's look at this first one. Okay, again, as usual, what you want to do to start is you want to identify the parent function. The parent function in this case is 1/2 to the power of x. And really, to do this correctly, we should put it in a bracket so there's no confusion about what is to what power here. Okay, that's the parent function. That 1/2 is not a parameter. It's part of the parent. Now, when you're making an exponential, one of the things that's a little bit more difficult or different, I don't think it's difficult, but it is different than using a regular, doing a regular function, is that you can't just memorize all the parent function. You can't just memorize all the points, right? Because every parent function is different. So let's say we have x, and here we have f of x, and Okay, now my parent function, right? Here's the trick to how you make the parent function. Okay, x is -2, -2, -1, 0, 1, and 2. Okay, so no problem there. Now f, okay, is 1 over b squared, then 1 over b, then 1, then b, then b squared. Okay, now you don't necessarily need all 5 points for a function. For example, 1 over b squared is often going to be very, very small and may be difficult to draw. And 2 and b squared might be really big and difficult to draw. So at the minimum, you need these 3. But you can always use the extra 2 to check your work, or if you wanted to know any more. So let's do them in our case. Our function is 0.5, or 1/2, 0.5 to the x. So let's start with the easy one. it goes through 0, 1. Because there's no b in this point. Did you notice? This one is just always 0, 1 for every function. Now b is easy to get. That's just 0.5. b squared is 0.5 squared, which is 0.25. Okay, so we have those points. Now, what is b to the negative 1? So 0.5 to the power of negative 1, that's equal to 2. And 0.5 to the power of negative 2 is equal to 4. Okay, so these are the points I need on my parent function. Okay, so let's just quickly draw the parent function one more time. So here's my parent. Okay, so it was 4, 2, 1, 0.5, and 0.25. Okay, now in the middle column, I'm going to, what I'm going to do here is I'm going to take every x, and transform it into x over k plus d. Yikes. Okay, I'm going to do the same thing with y, and every y is going to become ay plus c. Now, of course, to do this, I'd like to know what a, k, d, and c are. So let's go back up to the question. I've identified the parent. Let's identify the parameters now. The parameters. Okay, a is 3. K is negative 1. D is 0, because there's no D there. And C is 2. Okay, again, this is where A is coming from. Okay, that's where A is coming from. This number, oh, well, I guess I can't highlight it, but that's K. This is C. Okay, and K and D are up here in the exponent. Now, K is the number that's multiplying X. D is the number that is subtracted from X. Okay, so let's go ahead now, and I can go down here, and I can make my transformation equation. So I start with negative 2. Okay, I divide it by k, which is negative 1, and then I add 0. That's all I'm doing. So negative 2 divided by negative 1 is positive 2. Negative 1 divided by negative 1 plus 0 is positive 1. 0 divided by negative 1 plus 0 is still 0. 1 divided by negative 1 plus 0 is equal to negative 1. And 2 divided by negative 1 plus 0 is equal to negative 2. So here are my new x coordinates, 2, 1, 0, negative 1, negative 2. Okay? Now I'm going to look for my y coordinates. So a is 3 and c is 2. So start with the first coordinate. 4. 3 times 4 plus 2 is equal to 14. 3 times 2 plus 2 is equal to 8. 3 times 1 plus 2 is equal to 5. 3 times 0.5 plus 2 is equal to 1.5 plus 2 is 3.5. And finally, 3 times 0.25 plus 2 is equal to 2.75. Okay, so those are all the points I have. So my points are 214, 18, 05, negative 1, 3.5, and negative 2, 2.75. Okay, so let's look at them. And I'm not going to use this anymore, I don't think. Well, whatever, I'll leave it open in case we need it again. So let's draw those points I said we needed. So 214. Okay, 18, 05, negative 1, 3.5, and negative 2, 2.75. Okay. Now looking at those points, I should feel pretty confident. They do look like an exponential function. Let's draw the function and make sure I did this right. So the function I was supposed to draw, remember, was 3 times 1/2 to the negative x plus 2. So 3 bracket 0.5 to the power of negative x plus 2. And you can see we've got this perfectly. And even this other point, the A point, right, is all the way up there. Now again, on your picture, you're not going to be able to fit that A point, right? It's too high. You could draw it up here in the open space or whatever, but the point I was making about the ones I drew in red, sometimes they're too small to draw easily, or or they're off the page or something. So the minimum is 3 points. Okay, the minimum is 3 points. I would recommend you do 4, but 3 is fine. Okay. Now it says we're supposed to sketch, so we've done that. We know the 5 points it goes through, and we can sketch it. We know the asymptote is y equals 2. Again, that comes from the fact that the c value is 2. So let's write down what we know here. So what we're supposed to do is clearly label 2 points on the graph. Okay, well, I don't think 2 is enough. I think you need more than that. Let's change this to 3 to 4 points on the graph. Then state the domain, range, y-intercept, and equation of the horizontal asymptote. All right, so looking at this equation, the domain is x belongs to, I think that thing is pretty easy to find. Yeah, okay. Belongs to real numbers. Okay, so every exponential is real numbers unless it's context, right? So XER is the domain. The horizontal asymptote is y equals 2. The range, okay, now the range is going to be y is any real number, because it's not dots, it's a curve, such that y is bigger than 2, right? So you can't cross the horizontal asymptote in a function like this. So it's any number bigger than 2. The y-intercept was located at 0, 5. Okay, so those are all the things that we needed, I think, what it said there. So domain, range, y-intercept, equation, the asymptote. Okay, so we did all that. Okay, let's draw one more, and then we'll move on to the other part. I'll leave this third one just as a practice one for you. You can just load GeoGebra to check. You know what? I'll help you get it started. I'll give you the parameters, and then we can go from there. You can do it from there. Okay, so here, right, let's identify everything in the question. A is -2. K is 1. D is -1. C is -3. The parent function, f of x, is 3 to the power of x. Okay, let's make the table for the parent function. So I'm just going to copy this for a sec. Okay, now the parent function always looks like what you see in this section. So let's find the y value on our graph. This would be 1 over 9, right? Because, right. 1 over 9, because our parent is 3 to the x, so our b is equal to 3. 1 over 3 squared is 1 over 9. Then you have 1 over 3. Here you always have 1, because anything to the power of 0 is always 1. Here you have 3, and here you have 9. Okay, so those are the points. Those are the points on the parent that we're going to work with. Now when you go to transform these points, okay, so again, you just draw a table while I delete all this stuff. I don't think there's a quick way of doing this without... Okay, so I'm going to adjust the table. So we're not dealing with 1/2 to the x anymore. We're dealing with 3. So we get 1/9, 1/3, 1, 3, and 9. Okay. Now every x is going to be divided by 1 and then plus -1. So I don't really need to divide something by, I mean, I can write it, divide by 1, but it doesn't really do anything. And then I'm going to subtract another 1. I get -3. Okay. Here I get -1 minus 1 is -2. Here, -2, sorry. Here I get 0 minus 1 is -1. 1 minus 1 is 0. And 2 minus 1 is 1. Okay, so here are all my new x coordinates. Now my new y coordinates. I need to take these numbers, multiply them by -2, and then subtract 3. So this one, -2 times 1/9 subtract 3 is going to give me, let's see, -2 over 9 take away 3 is negative 3 and 2/9. And maybe just for a to make it an improper fraction, I'll just write negative 29 over 9. Remember, 3 over 3, a whole 3 would be 27 over 9, and then there are 2 more, so I get 29. Here, okay, so I get negative 2 times 1/3, take away 3. That is negative 3 and 2/3, which is equal to negative 11/3. Okay. Here I get negative 2 times times 1, take away 3, which is negative 2 take away 3 is negative 5. Here I get negative 2 times 3, take away 3, which is negative 9. And here I get negative 2 times 9, take away 3, which is negative 21. Okay, so once again, the points I think I need are negative 3 and negative 29 over 9, negative 2 and negative 11 over 3, negative 1 and negative 5, 0 and negative 9, and finally 1 and negative 21. Okay, so let's just plot those points here. Okay, so let's move A to make it negative 3, negative 29 over 9. B is going to be negative 2, negative 11 over 3. C is going to be negative 1, negative 5. D is going to be 0, negative 9. E is going to be 1, negative 21. Okay, now obviously the function I drew last time is no good, but this does look pretty good for an exponential, right? It looks like it grows really rapidly on one side and then approaches an asymptote on the other. The asymptote, we know, is going to be given by the c value, which is negative 3. So the horizontal asymptote is always the same thing. It's y equals c, which in this case is y equals negative 3. So let's draw that. So y equals negative 3. You can see that's a pretty good, that looks right in terms of what this function is doing. Let's delete that and that. The domain is going to be anything. The range, so the domain is XER. The range is going to be YER as long as y is less than negative 3, right? It has to be underneath that asymptote. The y-intercept, we said, is 0 and negative 5, right? Sorry, 0 and negative 9. I was looking at the wrong thing. Negative 9. Okay, so let's draw the equation now and see if it goes through all our points. So negative 2, 3 to the power of x plus 1, take away 3. So negative 2, bracket, 3 to the power of bracket x plus 1, take away 3. And you can see it's perfect, right? It goes through all 5 of them. It has the right asymptote. Everything we drew is perfect. So I'm going to get you started on C, but I'm not going to do it. You can do it and check it on GeoGebra. If you have problems, raise them, ask me. Let's go through this one quickly. A. We need an A, a K, a D, and a C. And even before we do that, we need to know what's f of x. In this case, f of x is 3 to the x again. That's the parent. Remember, the parent is whatever the base is to the power of x. So I can see the base is a 3. It's raised to the power of x. So that's the parent function. It would have the exact same table as the one I drew here. So you can just reuse that table if you wanted. Now, a little bit of a trick here. You can see there's no a value, so that's 1. The c value is easy, that's 1. The k value is easy, that's 0.5. The d value is 2. And you'll be looking at this going, where do you see a 2? I don't even see a 2 in that equation. Remember, d is the first thing that happens to x. So 0.5x minus 1, which is what the exponent is in this case, you need to write that as 0.5 bracket, and then you have x minus 1 over 0.5, and it turns out that that is equal to 2. Okay, so in this case, your d is actually a 2. Be careful about this. D must be in the bracket and must occur before k. Okay? So this is what this says. You might need to factor the exponent to see the transformations. It's just a reminder about factoring it. Okay, let the parent function be 2 to the x. For each function that follows, state the transformations, state the y-intercept, state the domain and range. All right, so state the transformations. Let's write down the parameters first. A is -3, k is 1, d is 0, c is 1. The parent is 2 to the x. I mean, I already said that, but let's just refresh it anyway. Let's describe the transformations. Again, you describe the transformations in the order you see them. A, then k, then d, then c. So let's describe A. So f of x would be reflected in the x-axis and vertically stretched by a factor of 3. Okay? It wouldn't have any horizontal stretch or compression, so I'm going to ignore that. No horizontal shift left to right, I'm going to ignore that. I'm going to then say f of x would be vertically shifted 1 unit up. That's it. That's what this does. Now it says state the y-intercept. Now the y-intercept of any equation is equal to a plus c. Okay, and why would that be? Well, remember, every single function has 0, 1 on it. So if you transform 0, 1, you're going to get, some new you're going to get x over k plus d, so whatever x and d are. Sorry, I just want to make sure I'm not making a mistake here. I think I actually might be making a mistake. Yeah, because this one shifted over and the y-intercept shifts over. So let's not do that. Let's not do that. The easiest way to find the y-intercept is just to find 0 and f of 0. Not f of 0. Let's call it g of 0 because g is the transformation here. Okay, so how do I find? So all I have to do here is just plug in 0, right? So I plug in 0, I get y equals -3 times 2 to the power of 0 plus 1. Y equals -3 times 1 plus 1. Y equals -2. So this would be the y-intercept would be located at 0 and -2. The horizontal asymptote would be located at y equals the value of c, which is 1. So remember, this is coming from y equals c. This is coming from 0 and f of 0. Okay, so that's just how I did that. Just find the point f of 0 and tell me what it is. For the asymptote, you just say y equals c, and that will always be right. State the domain and range. So the domain is x belongs to any real number. The range, now you have to think a little bit about the range, right? You're always going to say y belongs to any real number, and then we're going to say y is either greater than c or less than c. In our case, I'm going to say less than c, because I can see that this negative here is reflecting my function so that instead of going up, it's going down. So it's going to be underneath. So since a is negative, the function is underneath the asymptote. Okay? I'm just remembering that. Okay, let's do a couple more. So here, this first one. Once again, the parent function is still the same, so it's still, this is 2b, right? So it's still the same equation. So the parent function is still 2 to the x. The a value and so on. A value is -1/2. K value is negative 0.5. D value, I'm going to leave for a second. C value is negative 1. Again, to get the D value, I need to take this negative 0.5x plus 4, and I need to factor out the negative 0.5, and it turns out when I do that, I get D as a positive 8, which is not obvious from looking at it, right? You got to take this extra step to see what happened to D. Okay, let's describe this one. So f of x would be reflected in the x-axis and vertically compressed by a factor of 1/2. F of x would be reflected in the y-axis and horizontally stretched by a factor of 2. Again, that 2 is coming from the 1 divided by 0.5 equals 2, right? That's where I'm getting that from. F of x would be shifted 8 units to the right. F of x would be shifted 1 unit down. Okay, let's draw this one and you can see what I'm talking about. So the original function was f of x is 2 to the x. The new function is negative 0.5 f negative 0.5 x plus 4 minus 1. Okay, now it's not that easy to see. You could see it's been shifted down 1, that's obvious. It's been reflected up to down and also left to right. So that instead of growth, it is decay, right? It's approaching its asymptote instead of coming away from it. And it also is in the negative side of the graph instead of the positive side, right? Now shifted over by 8 units, that's very hard to tell on a graph like this. There's nothing we can really do here except, check by, subbing in a point and seeing if it works. So let's sub in a point. We know 0, 1 would be on the original. If we did this right, then 0 over k plus d and 1 times a plus c should be on the new graph, and you can see that it is. So, I know I have this right. Again, its domain, range, and asymptote. Quickly, its domain is let's just copy it. Just copy and paste this. No, okay, never mind. We'll type it out. Okay, so the y-intercept would be located at 0, f of 0, or g of 0, I guess I should say. In our case, that would be, where would that be? So if we sub in 0 here, we get negative 1/2 times 2 to the power of negative 0.5 bracket 0 minus 8 bracket bracket, and then all of that take away 1. So what happens here? We get negative 1/2, okay, 2 to the power of negative 0.5 times negative 8 is the power of 4, and then minus 1, and so we get negative 1/2 times 16, take away 1, which is negative 8, take away 1, which is negative 9. So I'm hypothesizing that the y-intercept is located at 0 and negative 9. Let's just have a look here. Looks good, right? 0, negative 9 looks good. The horizontal asymptote is y equals c, so c is negative 1. Just move this onto its own page. Horizontal asymptote is y equals c, therefore in this question it's y equals negative 1. Domain, XER, range, YER, provided that y is less than the negative 1. And again, it's less than because the a value is negative, and that means that the function is below its asymptote, which you can see here. Okay, I'm going to leave this one. I think you're capable of doing this one. Again, if you want to ask about it, please feel free to. Write an equation for the exponential function that has been transformed given the following transformations. Okay, so reflected on the x-axis, that means k is negative. vertically stretched by a factor of 3. That means A is 3. Okay. Horizontally translated 1 unit left, D is -1. So let's write the equation. We start with 2 to the x is the original equation, and then we're going to add the parameters. So we put a 3 at the front. Usually it's a good idea to put a bracket so that the 3 and the 2 is not, because like if you just do that, it just looks like 32 to the x. You don't really want that, right? So 3 bracket 2 to the power of x plus 1, right? Because D is a negative, so I'm going to write x plus 1. And actually, to fix that up, I need a negative here because k is supposed to be negative. And then that D is in a bracket like so. Okay, so there's your answer. So this graph, okay, let's look at it. It would be stretched by a factor of 3 vertically. It would be reflected in the x-axis. I just realized I've done this wrong. Sorry, this is not the k reflects it in the y-axis. I'm sorry, that's a mistake. So this is wrong. Reflect in y-axis. So what I'm going to do is I'm just going to strike through that. So that's wrong. What I should have said is A is negative. So A should be -3. Okay, so now let's just correct my answer. -3 there, and this no longer has to be negative. So now I have reflected in the x-axis, that's the -A, vertically stretched by a factor of 3, that's A being 3, and then horizontally translated 1 unit left, that's D being up here. Okay, final thing for the day. Reflected in the y-axis, okay, this is what I should have said last time. K is negative, horizontally compressed by a factor of 1/2. K equals 2. Remember, in the sentence, you always get 1 over K. So in your equation, K is 1 over whatever's in the sentence. Vertically translated 5 units down, C is -5. So let's write the equation. G of x is equal to 2 to the power of -x, and then with a -5 at the end. Okay, so with transformations, make sure you do them in order. Do A, then K, then D, then C. You can't be wrong. A, K, D, and C all change the shape of the graph, and they all depend on the parent. The parent in this unit is different for every question. The parent needs you to understand what B is, and that goes into your original table. The domain is always XER because every exponential has an unlimited domain unless you're talking about a context. The range is either above the asymptote or below the asymptote. It depends. So if A is positive, you're above the asymptote, you're y greater than C. If A is negative, you're y less than C. The asymptote itself is y equals C, and some transformations can easily be written using different bases. This is a really, really good point. For example, instead of drawing 2 to the 4x, you could also just draw 2 to the 4 to the x. Right? And 2 to the 4, we know, is 16. And so instead of drawing 2 to the 4 to the x, you could just draw 16 to the x, which is really kind of an interesting property that these things have, right? Let's just demonstrate that quickly. 2 to the 4x is there, and then watch when I draw 16 to the x, it's the exact same graph, right? So maybe you could look at this question and go, I could do this with a k value of 4, or I could just do it with no k value and change the base to 16, right? So sometimes that makes questions easier too if you can do that. You never need to do that. Well, I shouldn't say never, but you don't often need to do that. But if you do see how to do it, it can help you. Okay, so again, any questions today, please post to the site. I left a few for you to do. I want you to try them. If you're not sure if you've got them right, feel free to ask me. That's what I'm here for. And yeah, there'll be more information about the end of this unit soon.